A point of infinite density lurks in the void, where gravity overpowers light itself. Black holes are real cosmic engines, and their study has fundamentally rewritten the laws of physics. By the end of this journey, you will understand 30 discoveries that completely reshaped modern science. We will explore how these dark giants challenge the nature of reality and what happens to information that falls into their grasp. Black holes force us to question if space and time are truly what we think. What does it mean for our universe that such profound mysteries exist in the darkness? The equations for these cosmic monsters were born in the trenches of a world war. Karl Schwarzschild, a German physicist, found a moment of profound clarity amidst the chaos of the Russian front. With paper and pen, he solved Albert Einstein's complex new equations for general relativity. His answer described a reality so warped that space and time themselves break down. At the heart of this warped region lies a point of infinite density, a singularity, a place where the known laws of physics simply cease to apply. And surrounding this point is a perfect spherical boundary, the event horizon. This is the point of no return, the ultimate cosmic border. Once anything crosses that invisible line, not even light can escape the pull. Schwarzschild had given the world the first rigorous mathematical description of a black hole, though the name would not exist for decades. His solution showed that if a star is massive enough, its own gravity could cause it to collapse into this state of ultimate density. The escape velocity from such an object would exceed the speed of light, the universe's ultimate speed limit. This was not just a theoretical curiosity. It was a direct, unavoidable consequence of Einstein's theory of gravity, forcing physicists to confront the most extreme implications of their own ideas. How does a universe that allows for such terrifying objects even function? This initial mathematical insight was so radical that many, including Einstein himself, doubted it could ever be real. Yet it paved the way for the next great theoretical challenge, forcing science to ask what happens when a star dies. That mathematical ghost from the trenches finally found its physical form in the constellation Cygnus. High above our atmosphere, in the silent realm of space, early X-ray telescopes picked up a signal. It was not a gentle twinkle of visible light, but a violent, screaming beacon of high-energy radiation. Astronomers had discovered Cygnus X-1, a mysterious object pouring out X-rays with immense power. The source was a binary system, a cosmic dance between a brilliant blue supergiant star and something utterly dark, an unseen companion whose presence was felt only by its ruthless gravity. This invisible partner was actively pulling material away from the giant star. As this stolen gas spiraled down into an incredibly hot, whirling disk, it heated to millions of degrees, a process so energetic it lit up the X-ray sky. Here was the first strong candidate for a black hole, no longer just an equation on a page, but a real object in our galaxy. By carefully studying the orbit of the visible star, scientists could weigh the invisible one. The numbers were staggering. This dark object possessed a mass several times greater than our own sun, far too heavy to be any known type of dead star, like a neutron star. The only thing that could be so massive, so dark, and so compact was a black hole. This was the moment theory became reality. We could finally point to a specific coordinate in the night sky and know that a gravitational monster lurked there, a place where space and time were torn apart. The confirmation of Cygnus X-1 did more than just prove one object existed. It flung open the cosmic doors, igniting a new era of hunting for these dark giants. It proved that black holes were not rare anomalies, but natural endpoints for the lives of the most massive stars. This discovery forced a profound shift in our cosmic perspective. What does it mean for our place in the universe when we can confidently identify such profound darkness? It means we are no longer just observers of a peaceful cosmos, but explorers of a dynamic and sometimes violent reality. Even the most perfect cosmic prison cannot hold everything forever. Stephen Hawking proposed a thought that seemed to defy the very nature of these dark giants. In 1974, he introduced the idea of Hawking radiation, suggesting that black holes are not truly black. They possess a faint, theoretical glow, a slow leak of energy that seals their ultimate fate. This startling concept bridges the vast chasm between the cosmic laws of gravity and the bizarre rules of the quantum world. It all begins with the quantum foam, a seething sea of potential at the smallest scales. Here, pairs of virtual particles constantly flicker into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other. Normally, this dance leaves no trace, but at the very edge of a black hole's event horizon, this delicate balance is shattered. If one particle of the pair falls across the point of no return, its partner is left stranded, robbed of its chance to vanish. This orphaned particle escapes, carrying real energy away into the universe. To conserve energy, that stolen power must come from somewhere. It comes from the black hole itself, slowly reducing its mass. This means a black hole is not a permanent fixture. It has a temperature, an incredibly low one, but a temperature nonetheless. And like a piece of coal cooling in the void, it will eventually evaporate, fading out of existence over trillions upon trillions of years. Hawking's work showed that even the most immutable objects in the cosmos are subject to the strange decay of quantum law. This revelation created one of the most profound puzzles in modern physics. If a black hole evaporates, what happens to all the information about the stars, gas, and atoms that fell into it? According to quantum mechanics, information can never be truly destroyed. But according to Hawking's original calculations, it would be lost forever, scrambled into meaningless radiation. This is the black hole information paradox, a direct conflict between the pillars of general relativity and quantum mechanics. How can something so massive and seemingly permanent simply fade away, seemingly erasing the history of everything it consumed? This quantum leakage is not a minor detail. It is a screaming clue that our understanding of reality is incomplete, pointing toward a deeper, unified theory of quantum gravity waiting to be found. The faint tremor lasted for only a fraction of a second, a cosmic vibration that had traveled for over 1 billion years. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, felt this subtle shudder in the fabric of reality. It was the first direct detection of gravitational waves, ripples in spacetime predicted by Einstein a century earlier. The source was a cataclysm of almost unimaginable scale, two black holes locked in a final, fatal dance. For millions of years, they had spiraled closer, and in their last moments, they whipped spacetime itself into a storm, merging into a single, more massive object. The signal LIGO captured was the literal sound of that collision, a quiet chirp that confirmed the existence of these binary systems and gave us an entirely new way to perceive the universe. Before this, our view of the cosmos was built entirely on light, from radio waves to X-rays. Now we could listen. The precise shape of the detected waves was a perfect match for the simulations of black hole mergers. This was not just supportive evidence, it was irrefutable proof of their existence and dynamic behavior. These events are completely dark to traditional telescopes, emitting no light at all. Their story is written only in the warping of spacetime itself. This discovery unveiled a hidden population of black holes, giants that had lived and died in the dark, completely unknown to us. The dawn of gravitational wave astronomy has transformed our perception of the cosmos from a silent movie into a rich symphony. What does it mean that we can now hear the echoes of colliding giants from the deepest voids? It reveals a universe far more active and violent than we ever suspected, humming with the secret motions of immense masses. This new sense forces us to ask what other invisible phenomena are creating a constant, inaudible rumble all around us. Deep in the heart of our own Milky Way, a silent titan dictates the motion of the stars. For decades, astronomers patiently tracked a handful of stars in the crowded galactic center, watching them trace frantic, looping orbits around an empty point in space. One star, known as S2, completes its breakneck journey in just 16 years, reaching speeds of over 15 million miles per hour at its closest approach. The only force that could whip a star around with such violence is the gravity of something incredibly massive and incredibly small. That something is Sagittarius, a star, a supermassive black hole with a weight of 4 million suns. This was not a distant, hypothetical object. It was a gravitational monster living in our own cosmic backyard, its presence confirmed not by light, but by the graceful, predictable dance of the stars it holds captive. This discovery transformed our understanding of galaxies. Sagittarius, a star, is not a rare anomaly. We now know that nearly every large galaxy has its own supermassive black hole anchored at its center. The mass of this central beast is intimately tied to the properties of the galaxy itself, as if the galaxy and its black hole grew up together, influencing each other's destiny. This co-evolution suggests that these dark engines are not just passive occupants. They are active architects shaping the formation of stars and the very structure of their cosmic homes. Their powerful gravity can funnel vast amounts of gas, triggering brilliant bursts of new stars or, in some cases, quenching star formation entirely. Having one so close to us provides an unparalleled laboratory. We can test the limits of Einstein's gravity by watching how stars behave in its extreme grip, and we can study how matter behaves as it spirals toward the point of no return. So what does it mean to live in a galaxy with such a heart? It means our Milky Way is not a static collection of stars, but a dynamic system governed by a central, invisible force. Our galactic home has a silent gravitational pulse, a reminder that even in the quietest corners of the cosmos, immense power lies dormant, waiting to be understood. This paradox cuts to the very heart of what we know about reality. If a black hole vanishes, what happens to the story of everything it ever consumed? Every atom, every particle, every unique bit of information that fell in seems to be erased from the universe. Yet quantum mechanics, one of our most successful theories, insists this is impossible. It states that information is never truly lost, only scrambled and transformed. This is the black hole information paradox, a direct and terrifying conflict between the two pillars of modern physics. On one side, general relativity describes the black hole's gravity and its smooth, featureless event horizon. On the other, quantum mechanics demands that the information about what fell in must be preserved somewhere. For decades, physicists have wrestled with this, and their proposed solutions are as mind-bending as the problem itself. One leading idea suggests that the event horizon is not a smooth, simple surface. Instead, it might be a chaotic firewall of intense energy, a wall of fire that instantly incinerates anything crossing it, preserving information by never letting it truly enter the black hole in the first place. Another, even more radical proposal comes from the holographic principle. This theory posits that all the information describing the three-dimensional volume inside a black hole is actually encoded on its two-dimensional surface, the event horizon like a cosmic DVD. The three-dimensional world we perceive could be a projection from that flat, encoded surface. If this is true, then the information never falls into the singularity. It is smeared across the horizon, and as the black hole evaporates via Hawking radiation, that information is slowly and chaotically leaked back out into the universe. The radiation would not be random, but would carry a subtle, encrypted imprint of everything that was lost. This ongoing debate is not just academic. It is a powerful signal that our understanding of space, time, and information is fundamentally flawed or incomplete. The paradox forces us to question whether information is the most fundamental building block of the cosmos, more basic than matter or energy. Resolving this conflict likely requires a theory of quantum gravity, a framework that can seamlessly merge the world of the very large with the world of the very small. The information paradox is more than a puzzle. It is a beacon guiding us toward the next great revolution in physics and challenging our most basic assumptions about what it means for something to exist. That dark shadow we had only ever mapped through mathematics and gravitational influence finally came into view. A global network of radio telescopes, synchronized to act as a single instrument the size of our planet, turned its collective gaze toward a galaxy 55 million light-years away. Their target was the supermassive black hole at the heart of Messier 87, a cosmic giant with the mass of 6.5 billion suns. The result, unveiled in April 2019, was an image that instantly became an icon of modern science. It was not a picture of the black hole itself, for that is impossible, but of its shadow, a perfect dark circle set against a brilliant, swirling ring of fire. This bright halo was the accretion disk, matter heated to billions of degrees as it spiraled toward the event horizon. The darkness at the center was the point of no return, the event horizon, where space-time is so warped that light simply orbits the abyss before vanishing forever. The shape and size of that shadow matched the predictions of general relativity with stunning precision, confirming Einstein's theory in the most extreme gravitational environment imaginable. This was not an artist's impression or a computer simulation. It was direct visual proof of the structure of a black hole. The achievement was a testament to human ingenuity and global cooperation, a project that required scientists across continents to work in perfect harmony, processing a volume of data so immense it had to be shipped on physical hard drives. For the first time, an object defined by its ability to trap light was made visible to all of humanity. What does it mean to see the unseeable? It transforms an abstract mathematical concept into a tangible cosmic reality, a place we can point to and say, that is a black hole. This single image did more than confirm a theory. It gave the world a shared symbol of exploration, a profound reminder that even the universe's darkest secrets can be illuminated by the persistent light of human curiosity. These brilliant beacons from the edge of time were first spotted as faint, star-like points of radio energy. In the 1960s, astronomers identified them as quasars, quasi-stellar radio sources, and their true nature was more astonishing than anyone had guessed. Each one was a cosmic lighthouse, shining with the light of 1 trillion suns, outshining the combined output of every star in their home galaxy. The only conceivable engine for such staggering power was a supermassive black hole in a state of violent feasting. This was the discovery of accretion power, the profound transformation of gravitational energy into pure light. As vast rivers of gas and dust spiral toward the event horizon, they do not fall in silently. They form a furious, whirling disk, a cosmic hurricane where particles collide at nearly the speed of light. Friction within this accretion disk heats the material to millions of degrees, causing it to glow with an intense, white-hot radiance that floods across the entire electromagnetic spectrum, from radio waves to X-rays. The efficiency of this process is breathtaking, converting matter into energy with a potency far greater than nuclear fusion. This revelation completely redefined black holes. They were not the passive endpoints of collapse, but could become the most energetic engines in the entire cosmos, their brilliance capable of shining across billions of light years. Quasars were the key that unlocked a deeper galactic mystery. Their immense luminosity allowed us to detect them in the most remote, ancient corners of the universe, revealing that supermassive black holes were not rare anomalies but common fixtures in the hearts of galaxies from the very beginning. Their light, which began its journey when the universe was young, tells us that these giants grew up alongside their galactic homes. This relationship is not one-sided. The black hole actively shapes its environment through powerful outflows and jets, a process known as feedback. These eruptions can sweep away the gas needed to form new stars, effectively putting a brake on a galaxy's growth, or they can trigger star birth in surrounding clouds. The supermassive black hole becomes a galactic regulator, its feeding habits dictating the future of its entire cosmic island. So how can an object defined by its darkness create the most brilliant light we can observe? The answer lies not in the black hole itself, but in the frenzied, luminous death spiral of the material just outside its grasp. The study of quasars illuminates a fundamental truth, that the greatest cosmic fires are often born from the deepest gravitational shadows. This radical simplicity is one of the universe's most profound and counterintuitive truths. A black hole, the end result of the most complex gravitational collapse imaginable, can be completely described by just three numbers: its mass, its electric charge, and its spin. This is the essence of the No-Hair Theorem. Whatever falls into a black hole, whether it is an entire star made of unique elements, a cloud of interstellar gas, or even a spacecraft, all of its intricate details are erased. The specific atoms, their chemical compositions, their shapes, all of that information is lost to the outside universe. The resulting black hole is defined only by how much it weighs, how fast it is spinning, and whether it holds any electric charge. It has no hair, no additional features to distinguish one from another. Two black holes with identical mass, spin, and charge are fundamentally indistinguishable, perfect cosmic twins. This means a black hole has no memory. It does not remember if it was born from a single massive star or from the violent merger of a dozen smaller holes. This presents a startling paradox of its own. We live in a universe that seems to cherish complexity and individuality, yet here, in its most extreme environments, it enforces a brutal and elegant simplicity. The No-Hair Theorem is a direct consequence of the equations of general relativity, which seem to demand that any bumps or irregularities on a forming black hole are radiated away as gravitational waves, leaving behind only a perfectly smooth, featureless object. This simplicity is a gift to physicists, allowing them to model the most ferocious objects in the cosmos with a handful of clean parameters. Yet this very simplicity creates a deep conflict with quantum mechanics, which insists that the information about what fell in must be preserved somewhere, somehow. If a black hole truly has no hair, then where did all that detailed information go? The theorem stands as a stark reminder that our two most powerful descriptions of reality are at war, and that the universe's preference for minimalism might be the key to unlocking a far deeper truth. What does it say about the fabric of reality that complexity can be so utterly erased, leaving behind only the purest gravitational essence? Spacetime itself is not a rigid stage but a fluid, dynamic entity, and a spinning black hole churns it like a cosmic whirlpool. This is frame dragging, a phenomenon predicted by Einstein's field equations where a rotating massive object literally pulls the fabric of the universe along with it. You can think of it as a spoon spinning in a vat of thick honey. The honey closest to the spoon is dragged around, creating a vortex that influences everything nearby. In the same way, a black hole's immense spin twists the empty space around its event horizon, forcing nearby matter and even the paths of light to follow its rotation. This subtle but profound effect, also known as the lens-Thirring effect, confirms that mass is not the only property that warps reality. Rotation leaves its own direct imprint on the cosmos. While the effect is incredibly weak around Earth, a sensitive satellite experiment named Gravity Probe B managed to detect it by monitoring the minute changes in the orientation of gyroscopes in orbit, providing a beautiful confirmation of general relativity right in our own celestial neighborhood. Around a spinning black hole, however, frame dragging is not subtle. It is a dominant, violent force that creates a region known as the Ergosphere. This is an oval-shaped zone of twisted spacetime that lies outside the event horizon. Within the Ergosphere, the dragging is so intense that nothing, not even light, can resist being swept along. It is impossible to stand still. This bizarre property leads to an astonishing possibility: the extraction of a black hole's rotational energy. A theoretical process proposed by the physicist Roger Penrose suggests that if an object were to enter the Ergosphere and split in two, with one piece falling past the event horizon and the other escaping, the escaping fragment could carry away more energy than the original object possessed. The energy bonus is stolen from the black hole's own spin, slowly breaking its rotation. This transforms our view of black holes from simple gravitational sinks into dynamic cosmic engines. They are not just consumers of matter and light, they are power plants capable of transferring their immense rotational energy to the surrounding universe. How does the spin of such an object shape the very space around it? It forges a cosmic maelstrom where the universe itself is set into motion, a swirling dance that powers some of the most luminous and energetic phenomena we can observe. A black hole is the universe's most perfect thermodynamic engine. This stunning connection emerged when physicists realized the equations governing these dark giants bore an uncanny resemblance to the fundamental laws of heat and energy. It began with a young graduate student named Jacob Bekenstein, who dared to ask a provocative question. If a black hole truly had no hair and could not remember what fell in, what would happen if you threw a box of hot gas, a high-entropy object, across the event horizon? From the outside, it would seem the total entropy of the universe had suddenly decreased, violating the second law of thermodynamics, which states that disorder always increases. Bekenstein proposed a radical solution. What if the black hole itself possessed entropy? He suggested that a black hole's entropy is not related to its volume, but to the surface area of its event horizon. The larger the black hole, the more surface area it has, and the more information it can potentially hold. This idea was initially met with skepticism, as a black hole with entropy must also have a temperature, and everyone knew that black holes did not radiate. Then Stephen Hawking made his famous calculation. He discovered that black holes do indeed have a temperature, an incredibly faint one resulting from the quantum effects at their boundaries. Hawking radiation provided the precise temperature needed to complete the thermodynamic picture. Suddenly, black holes were not just gravitational objects, they were thermal systems obeying their own perfect set of laws. The first law links a change in a black hole's mass to a change in its event horizon area, mirroring the conservation of energy. The second law states that the total area of all event horizons can never decrease, just like universal entropy. This was more than a curious analogy, it was a profound clue. it suggested that the vast three-dimensional space we experience might not be fundamental. What if spacetime is emergent like the surface of a lake, its smooth appearance arising from countless microscopic interactions happening at a deeper level? The event horizon could be a screen onto which the information about everything inside it is projected, a holographic storage system of ultimate efficiency. This thermodynamic bridge forces us to reconsider the very fabric of reality. Could the cosmos in its entirety be understood as a complex thermodynamic system, with black holes acting as its most fundamental and revealing components? The heat of a black hole's whisper-thin radiation hints that gravity and thermodynamics are two sides of the same cosmic coin. For decades, our cosmic census of black holes was oddly divided. We found small ones, the stellar mass remnants of dead stars, and we found the supermassive behemoths anchoring galaxies. But what about everything in between? The hunt was on for the missing middle child, the intermediate mass black hole. These objects are the cosmic middleweights holding the mass of hundreds to thousands of suns. They are the crucial link in a grand evolutionary chain. We first caught glimpses of them in the ancient, dense ball of stars known as globular clusters. The motion of stars at the very heart of some clusters was too fast, too erratic, to be explained by the combined gravity of the stars alone. Something dark and massive was lurking there, a gravitational anchor stirring the pot. Another clue came from brilliant, ultraluminous X-ray sources spotted in the outskirts of galaxies. These were not the faint flickers of small black holes, nor the roaring engines of supermassive ones. Their intense energy output pointed to a mid-sized powerhouse, a black hole large enough to pull in vast amounts of gas and shine with a distinctive, powerful light. The most compelling evidence arrived through the music of gravitational waves. LIGO and Virgo have now heard the collisions of black holes in this intermediate mass range, confirming their existence through the ripples they create in spacetime. Finding these objects completes the black hole mass spectrum. It suggests a continuous family tree from the small to the unimaginably large, but their true importance lies in their potential role as cosmic seeds. How does a galaxy grow a supermassive black hole at its core so quickly in the early universe? It might start with one of these intermediate mass holes, a ready-made building block left over from the chaotic dawn of time. This seed could then merge with others and voraciously feed, ballooning into the giant we see today. They are the missing links in the story of galactic evolution. So how do these mid-sized monsters form? They might be the ancient remnants of the universe's very first gigantic stars, or they could be the result of a runaway chain reaction, where multiple stellar mass black holes in a dense cluster merge together over eons. Each scenario writes a different chapter in the history of our cosmos. Unraveling their origins does more than just fill a gap in a catalogue. It reveals the fundamental building blocks of galactic centers and tells us how the largest structures in the universe were assembled, piece by dark piece, from the very beginning. A black hole's spin can launch energy across the cosmos. This is the Blandford-Zenagic process, a model that reveals how these dark giants become cosmic power plants, generating jets of matter and energy that stretch far beyond their host galaxies. Imagine a colossal, spinning black hole, its immense gravity pulling in surrounding gas to form a superheated accretion disk. But the true power lies not in the disk alone, but in the magnetic fields frozen within it. As the black hole rotates, it drags the very fabric of spacetime around it, twisting these magnetic field lines into a tightly wound, colossal coil. This structure acts like a cosmic slingshot, channeling some of the infalling material and accelerating it outward along the black hole's rotational axis. The result is a pair of jets, narrow beams of plasma hurtling away at nearly the speed of light. These are not gentle streams, they are relativistic jets carrying enough energy to plow through interstellar space for thousands, even millions of light years. They can heat vast clouds of galactic gas, preventing it from cooling and collapsing to form new stars. In this way, a black hole does not just consume. It governs, acting as a galactic regulator that can either trigger or quench star formation across an entire galaxy. The discovery of this mechanism fundamentally changed our view of black hole influence. It showed that their impact is not limited to the crushing pull of gravity right at their edge. Through the Blandford-Zenagic process, a black hole can project its power across unimaginable distances, shaping the evolution of its cosmic home. How can a silent, dark object create such brilliant, focused fury? The answer is written in the language of twisted spacetime and magnetic force, a reminder that the universe's most dramatic displays often arise from the most invisible and fundamental interactions. The flicker of a distant X-ray light can signal a cosmic feast. In the quiet darkness of our galaxy, stellar mass black holes often exist in binary partnerships, locked in a gravitational embrace with a normal star. These systems can remain dormant for years, until a subtle shift in their orbit allows the black hole's gravity to reach out and steal matter from its companion. This stolen gas does not fall directly into the abyss. It spirals inward, forming a seething, luminous accretion disk that heats up to millions of degrees, erupting in a sudden and brilliant outburst of X-rays. Astronomers call these events X-ray nova, transient beacons that flare brightly and then slowly fade, revealing the presence of a hidden black hole. Each of these eruptions is a unique opportunity. By carefully analyzing the X-ray light, scientists can perform a kind of cosmic autopsy on the event. The spectrum of the radiation reveals the composition and temperature of the swirling disk, while subtle flickers in its brightness, a phenomenon known as timing, can be used to measure the black hole's spin and mass with remarkable precision. These observations have uncovered a hidden population of stellar mass black holes drifting silently through the Milky Way. Each binary system tells a story of stellar life and death. The very existence of these pairs places strict constraints on how the original massive star exploded. The supernova kick must have been just right, not so violent that it tore the binary apart, but forceful enough to leave behind a black hole in a stable orbit. This makes each system a fossil record of a cataclysmic stellar death. What can the flickering light from this cannibalistic dance tell us about gravity itself? These binaries are natural laboratories, allowing us to watch matter behave in the most extreme gravitational fields imaginable, testing the predictions of general relativity in real time. They offer a front-row seat to the physics of accretion, the fundamental process that powers the most luminous objects in the universe. The study of these feeding frenzies illuminates the delicate balance of cosmic forces, showing how even in the darkness, the gravitational pull of a black hole can paint the sky with brilliant, fleeting light. But what if the universe's ultimate breakdown could be exposed for all to see? Roger Penrose proposed a profound safeguard known as the cosmic censorship hypothesis. This is the idea that nature possesses a deep-seated aversion to what physicists call a naked singularity. A singularity is that point of infinite density at the heart of a black hole, where the known laws of physics cease to function. Penrose conjectured that every single one of these catastrophic endpoints must be permanently veiled behind an event horizon, forever hidden from the outside universe. Think of the event horizon as a cosmic quarantine zone, an impenetrable curtain drawn around a point of infinite chaos. This hypothesis is not a proven law, but it is a foundational belief that allows physicists to do their work with confidence. It ensures that the unpredictable, lawless realm of the singularity cannot reach out and influence our predictable cosmos. Without this cosmic sensor, the very fabric of reality could unravel. A naked singularity could theoretically allow for violations of causality, where effects precede their causes, creating paradoxes that would make the universe an incomprehensible and untrustworthy place. The orderly flow of time and the reliable chain of cause and effect we depend on would be thrown into question. The ongoing search for a counterexample, for a crack in this cosmic armor, drives cutting-edge research into gravitational collapse and the frontiers of quantum gravity. Is the universe actively protecting us from its own most terrifying secrets? This elegant hypothesis maintains the stable stage upon which all of physics is performed, a silent guardian ensuring that the deepest darkness remains safely contained, allowing the light of predictability to shine throughout the rest of the cosmos. The very first moments of the universe may have forged black holes from pure chaos. Unlike their stellar descendants born from collapsing stars, these primordial black holes are theoretical relics, crystallized from the unimaginable densities that followed the Big Bang. This concept opens a staggering possibility. The mass of these ancient objects would not be constrained by the life cycle of a star. They could be almost anything from the size of a small asteroid to larger than 1,000 suns, each one a frozen knot of the early universe's extreme physics. Their potential existence forces us to reconsider the very composition of the cosmos. What if a significant portion of the mysterious dark matter, the invisible glue holding galaxies together, is not an exotic particle but a vast population of these primordial holes drifting unseen through the darkness? They would be the universe's ultimate fossils, carrying information about a time before the first stars ever flickered into being. The hunt for these ghosts is a masterclass in cosmic ingenuity. Astronomers search for their subtle signatures through a phenomenon called microlensing. If an invisible primordial black hole were to pass directly in front of a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily brighten in a very specific way. We are also listening for them with gravitational wave observatories, hoping to catch the unique chirp of two asteroid mass black holes merging in the void. Even the faint afterglow of the Big Bang itself, the cosmic microwave background, could bear the scars of their early influence. A confirmed detection would be more than just adding a new class of object to the cosmic zoo. It would be a direct window into the highest energies and most extreme conditions we can possibly probe, a glimpse of physics at energies far beyond what any particle collider on Earth could ever achieve. The universe may be filled with these silent travelers from the dawn of time, and finding just one would forever change our story of how everything began. That tranquil boundary might be a lie, the very point of no return. The event horizon we have imagined as a smooth and silent gateway could instead be a wall of fire. This is the black hole firewall paradox, a modern and deeply unsettling twist in the quest to understand what happens to information. The proposal is as radical as it sounds. To preserve the sacred quantum rule that information cannot be destroyed, some physicists suggest that the event horizon must be a seething inferno of high-energy particles. Anything crossing it would not experience a gentle passage into warped spacetime. It would be instantly vaporized. This firewall would solve the information paradox by ensuring that information never actually enters the black hole. Instead of being lost inside the singularity, it is scrambled and encoded into the fiery radiation at the horizon, potentially recoverable as the black hole evaporates. But this solution comes at a tremendous cost. It directly violates a cornerstone of Einstein's general relativity, the equivalence principle. This principle assures us that a free-falling observer would feel nothing special as they cross the event horizon. There should be no local sign, no dramatic change, no wall of fire. From their perspective, it is just another point in space. The firewall shatters this elegant idea, suggesting that the horizon is not tranquil but violently singular. This paradox has ignited one of the most intense debates in modern theoretical physics, forcing a complete re-examination of quantum field theory in the severely curved spacetime around a black hole. The core question is stark and simple. Which of our fundamental theories must break? Does quantum mechanics demand a firewall, proving that Einstein's smooth spacetime is an illusion at the boundary? Or does the equivalence principle hold, meaning our understanding of quantum information is flawed in these extreme conditions? This is not a minor disagreement. It is a battle for the soul of physics at the precipice of a black hole, a clear signal that our current tools are inadequate. The resolution will not come from choosing one side over the other, but from a new, deeper understanding of how gravity and the quantum world truly unite. The serene horizon or the violent inferno, one of them must be an illusion, and uncovering the truth will reshape our conception of reality itself. The inner edge of that searing accretion disk holds a secret, written in the twisted light of iron. As gas spirals toward the point of no return, atoms of iron within it are heated to such extremes that they scream out in X-rays. This is not a random signal. It is a specific, recognizable fingerprint of atomic energy. But as these X-rays race away from the black hole's gravitational grip, they are not the same. The immense gravity warps their very energy, stretching their wavelengths in a process called gravitational redshift. The spin of the black hole adds another layer of distortion, dragging the inner disk so close that the X-rays are smeared across a range of energies. By meticulously decoding this smeared signature, astronomers can perform a kind of cosmic forensics, measuring exactly how fast the black hole is spinning. The results are breathtaking. Many black holes, both stellar mass and supermassive, spin at velocities approaching the cosmic speed limit set by general relativity. They are nature's ultimate tops. This frantic rotation tells a specific story about their past. A black hole that grows primarily through chaotic, random mergers will have its spin slowed and redirected, like a top being bumped from different sides. But a black hole that has enjoyed a steady, prolonged diet of gas from a consistent direction will be spun up to incredible speeds, its rotation accelerated by the incoming material's angular momentum. So the spin is a historical record, a fossil of how the black hole grew over billions of years. How does this dizzying rotation influence its behavior? A rapidly spinning black hole stores immense energy in its whirl, energy that can be tapped through processes like flame dragging to power colossal jets. Its spin also defines the very shape of the space around it, altering the innermost stable orbit and determining how close matter can spiral before it plunges inward. This makes a spinning black hole a more efficient engine, converting a greater fraction of infalling mass into pure energy. The ability to measure spin through X-ray reflection is a direct test of general relativity in the most violent gravitational fields imaginable, probing the spacetime geometry just outside the event horizon. It confirms that the universe's most destructive objects are also dynamic, rotating engines, their histories written not in stone, but in the distorted light they leave behind. A supermassive black hole is the tiny, beating heart of a galactic giant. We now understand that these dark engines are not passive occupants, but active architects shaping the very galaxies they inhabit. The evidence for this profound connection lies in a series of cosmic correlations. astronomers found a remarkable link between the mass of a galaxy's central black hole and the properties of the surrounding stellar bulge, the dense cloud of stars at its core. The more massive the black hole, the larger and more massive the bulge. This is not a coincidence. It is the signature of a symbiotic relationship, a dance of growth that has unfolded over billions of years. The black hole and its galaxy grew up together, their fates intertwined. This co-evolution is governed by a process known as feedback, a cycle of cosmic construction and destruction. When a black hole actively feeds, it does not just glow brightly as a quasar. It can unleash tremendous outflows of energy and matter, powerful winds and jets that surge through the galactic core. These outflows act like a cosmic thermostat for star formation. They can heat vast reservoirs of cold gas or blow them entirely out of the galaxy, robbing it of the raw material needed to make new stars. In this way, the black hole quenches star birth, putting a brake on the galaxy's growth and preventing it from becoming overly large. Conversely, when galaxies collide in a monumental merger, the resulting chaos funnels immense amounts of gas toward the central black hole, igniting a brilliant quasar. The same gravitational turmoil can also compress giant gas clouds, triggering a firestorm of new star formation, a starburst. The black hole's activity and the galaxy's star formation are two sides of the same cataclysmic event. How can an object millions of times smaller than its host wield such control? The answer lies in the efficiency of its energy output. The gravitational energy released by even a small amount of matter falling into a black hole is staggering, and when channeled into jets and winds, it can influence gas across the entire galaxy. This discovery has fundamentally rewritten the story of galaxy formation. Black holes are no longer seen as mere byproducts. They are essential regulators, integral to the standard model of cosmic structure. Their feedback sculpts the galaxies we see today, determining whether a galaxy becomes a featureless elliptical or a grand spiral like our own Milky Way. This reveals a universe governed by a complex interplay between gravity, radiation, and the flow of matter, where the smallest, darkest objects can dictate the destiny of the largest structures in the cosmos. A star's final moments can illuminate an otherwise invisible darkness. When one drifts too close to the gravitational pull of a supermassive black hole, it experiences a force more extreme than any other in the cosmos. The side of the star nearest the black hole feels a vastly stronger pull than the far side, and this difference stretches the star horizontally while compressing it vertically. This tidal force is so immense it overcomes the star's own gravity, pulling it apart into a long, thin stream of gas in a cataclysmic event known as a tidal disruption. The star is not swallowed whole, it is meticulously shredded. About half of this stellar debris is flung away into the void, while the rest is pulled into a chaotic orbit, eventually raining down onto the black hole. As this river of gas falls inward, it collides with itself, forming a swirling, superheated accretion disk that glows with a brilliant flare of radiation. This flash can outshine the combined light of every star in its host galaxy for months, shining across the electromagnetic spectrum from visible light to powerful X-rays. For astronomers, this is a rare and precious beacon. It reveals a supermassive black hole that was previously dormant and invisible, quietly resting at the center of its galaxy. The characteristics of the flare's light curve, how it brightens and fades over time, act as a cosmic scale. They allow scientists to calculate the black hole's mass with remarkable precision. The specific signatures in the light spectrum reveal the chemical composition of the devoured star, telling us whether it was rich in hydrogen or helium, offering a glimpse into its life before the catastrophic end. These events are more than just spectacular cosmic fireworks. They are fundamental laboratories. The entire process, from the initial stretching to the final glow of the accretion disk, tests the predictions of general relativity in an environment of wildly changing and incredibly strong gravity. Each tidal disruption event writes a unique signature in light, a detailed story of a star's demise and a black hole's awakening. What can the death throes of a star tell us about the silent monster that consumed it? Everything from its weight to its feeding habits is encoded in that fading flash, a temporary lighthouse in the dark, revealing secrets we could never see otherwise. This region of twisted spacetime is a cosmic whirlpool of pure energy. Just outside the event horizon of a spinning black hole lies the Ergosphere, a zone where the fabric of the universe is dragged around with such violence that nothing can stand still. Every object, even a particle of light, is forced to move with the rotating spacetime. Yet, unlike the event horizon, this region offers a narrow path of escape. It was Roger Penrose who realized this turbulent boundary could be exploited. He envisioned a particle entering the Ergosphere and splitting in two. If one piece falls into the black hole, it can be arranged to fall in a direction that slows the black hole's spin, while the other fragment escapes at tremendous speed. The escaping particle carries away more energy than the original particle brought in. This is the Penrose process, a way to mine a black hole's rotational energy. The bonus energy does not come from nothing. It is stolen directly from the black hole's momentum, gradually slowing its furious spin. This transforms our view of black holes from simple devourers of matter into cosmic power plants. The energy available is staggering, potentially far more efficient than nuclear fusion. While this is far beyond our current technology, the principle is a reality of physics. It suggests that a sufficiently advanced civilization might one day use a spinning black hole as its ultimate energy source, a battery holding the rotational power of millions of stars. Natural versions of this process might already be at work, powering some of the most luminous and explosive events we observe in the distant universe. This discovery fundamentally challenges the idea of black holes as purely destructive. They are not just endpoints, they are dynamic engines, and their greatest power is unlocked not by their mass but by their spin. What other secrets might be hidden within the whirl of a rotating universe? Virtual universes inside supercomputers gave us the first true glimpses of a black hole's face. Long before the Event Horizon Telescope captured its historic image, theorists were already building digital realms where they could bend spacetime at will. These are not simple animations, but full-scale simulations solving the complex equations of general relativity and magnetohydrodynamics, governing how superheated plasma behaves in the most intense gravitational fields imaginable. By feeding in different parameters like a black hole's spin or the rate of accretion, physicists could watch as a dark shadow and a brilliant photon ring emerged from the calculations. This was the theoretical prediction of what a black hole should look like, a crucial blueprint that told observers exactly what to search for in the sky. The simulations revealed that this shadow is not the event horizon itself, but a larger darkness created by photons that graze the black hole and are captured into unstable orbits, a perfect circle of nothingness magnified by the extreme bending of light. The intricate structure of the surrounding bright ring, they found, depends dramatically on the black hole's rotation and our viewing angle. A face-on view of a rapidly spinning hole looks different from an edge-on view of a static one. This means that by carefully analyzing a real image, we can essentially measure a black hole's spin and orientation from millions of light years away. These virtual laboratories also explore the violent dynamics of merging black holes. calculating the precise gravitational wave signals they produce and predicting if the collision could ignite any fleeting light in the surrounding gas. How do these digital proxies guide our search for real ones? They provide the essential dictionary we need to translate the raw, chaotic data from telescopes into a coherent understanding of physics at the edge. Without these simulations, the first image of a black hole would have been an indecipherable enigma. They are the indispensable testing grounds for our theories, allowing us to venture into the unforgiving physics of the abyss and return with predictions, forever blurring the line between the virtual and the actual cosmos. Nature itself seems to have drawn a line in the cosmic sand, forbidding black holes of a certain size. Between approximately 50 and 120 solar masses lies a mysterious void known as the black hole mass gap. This is not a failure of our observations, but a profound rule written into the physics of stellar death. The explanation lies in a stellar cataclysm of almost unimaginable violence, the pair instability supernova. In the final moments of a truly gigantic star, the core becomes so incredibly hot and dense that a bizarre transformation occurs. The energy of gamma rays, usually responsible for supporting the star against its own gravity, begins to spontaneously create pairs of electrons and their antimatter counterparts, positrons. This process is like removing the supporting pillars from a building. The radiation pressure that was holding the star up suddenly vanishes. Without that outward push, gravity wins in an instant and the core collapses violently. This collapse, however, does not lead to a quiet formation of a black hole. Instead, it heats the core to even more extreme temperatures, triggering a runaway thermonuclear explosion that fuses oxygen and silicon in a single, unstoppable blast. The star does not leave behind a dense remnant. It is completely and utterly obliterated, scattering its entire being back into the interstellar medium. This is why the mass gap exists. Stars that are massive enough to potentially form a black hole in this range are, in fact, doomed to self-destruct so perfectly that nothing remains. Gravitational wave observatories have provided stunning confirmation of this rule. The black hole mergers they have detected show a clear absence of components within this forbidden zone, just as the theory predicts. This discovery gives us a much deeper understanding of stellar life cycles. It reveals a delicate and precise balance between the inward crush of gravity and the outward fury of nuclear physics. The final fate of a star is a tug of war, and for stars in this specific mass range, the nuclear forces win in the most absolute way possible, leaving no trace behind. Why would the universe outlaw black holes of a certain weight? The mass gap is a cosmic signature, a fossil record of the most powerful stellar explosions possible, teaching us that even in death, stars obey a strict and elegant set of rules that shape the population of dark giants we can ultimately find. The flickering X-ray light from a feeding black hole is not random noise. It has a rhythm, a subtle, repeating pulse hidden within the chaotic glow of the accretion disk. Astronomers call these signals quasi-periodic oscillations, or QPOS. They are the cosmic heartbeats of a black hole, rhythmic brightness variations that rise and fall in a nearly regular cadence. These oscillations are not like the steady tick of a clock. Their quasi-periodic nature means the rhythm is almost, but not perfectly, regular, a sign of complex and violent physics at play. These pulses originate from the very edge of the abyss, from the innermost regions of the seething accretion disk where matter makes its final, frantic orbits before plunging across the event horizon. The specific frequencies of these oscillations are not arbitrary. They are dictated by the fundamental orbital rhythms of spacetime itself, shaped purely by the black hole's immense gravity. One key frequency is tied to the innermost stable circular orbit. the final point where matter can still circle the black hole before its inevitable fall. The location of this orbit is itself determined by the black hole's mass and spin. A faster spin pulls the orbit closer, raising the frequency of the oscillations. By carefully measuring these rhythmic pulses, astronomers can perform a kind of cosmic seismology. They can listen to the vibrations of spacetime to weigh the black hole and measure how fast it is spinning, all from the subtle patterns in its X-ray light. Different types of QPOS are thought to arise from different phenomena, like the precession of the entire inner disk, a slow wobble like a spinning top, or from resonances and instabilities within the swirling plasma itself. Each type of pulse provides a unique window into the conditions just outside the point of no return. This makes QPOS a powerful and versatile tool for testing the predictions of general relativity in the most extreme gravitational fields we can observe. They allow us to probe the dynamics of strong gravity in a way that complements the low rumble of gravitational waves from merging black holes. While gravitational waves let us hear the collision of giants, QPOS let us listen to the steady, rhythmic pulse of a single black hole as it feeds, a continuous vibration of spacetime itself. What secrets are hidden in these rhythmic pulses? They are a direct signal from the precipice, a coded message about the very nature of gravity and the final moments of matter in the universe. The very fabric of space might be a magnificent illusion. This is the heart of the holographic principle, a concept so radical it suggests our three-dimensional universe, with all its depth and volume, could be a projection from a two-dimensional surface. Think of the event horizon of a black hole not as a barrier, but as a cosmic hard drive. According to this idea, every bit of information about the stars and gas that fell into the black hole is not lost inside the singularity. Instead, it is perfectly encoded pixel by pixel on the two-dimensional surface area of the horizon. The three-dimensional space we perceive inside is a holographic projection of that data, much like a three-dimensional movie is projected from a two-dimensional film. This principle found its most precise mathematical form in a discovery from string theory known as the AD-SCFT correspondence. It proposes a perfect duality, a cosmic translation dictionary. A theory of gravity operating within a certain type of warped space called anti-de Sitter space is completely equivalent to a quantum field theory, a theory without gravity, living on its lower dimensional boundary. They are two utterly different descriptions of the same reality. This correspondence has become an incredibly powerful tool, offering profound insights into the black hole information paradox. It suggests that information is never truly lost behind the event horizon. It remains stored on the surface, and as the black hole evaporates through Hawking radiation, that information can, in principle, be decoded from the outgoing particles. This provides a potential pathway to resolve the paradox, preserving the laws of quantum mechanics even in the face of total gravitational collapse. The implications ripple out far beyond black holes, challenging our most basic assumptions about spacetime itself. If a volume of space can be described by a theory on its boundary, then dimensionality might not be fundamental. Our rich, three-dimensional experience of the world could be an emergent property, a hologram generated from a vast, interconnected network of quantum information living on a distant, two-dimensional surface. What does it mean for reality if the universe is ultimately a lower dimensional projection? The holographic principle does not just offer a new answer to an old puzzle. It completely redefines the question, suggesting that space, time, and gravity themselves may be secondary phenomena, born from the intricate entanglement of quantum data. This is not merely a new theory of black holes, it is a new lens through which to view the cosmos, transforming our understanding of what it means for anything to exist at all. The final moments of a black hole merger do not always end in a quiet rest. When two giants spiral together and become one, the universe itself can deliver a staggering blow. The new black hole recoils, kicked out of its home at a significant fraction of the speed of light. This phenomenon, a gravitational wave recoil, occurs when the merger is messy and asymmetric. If the two black holes have unequal masses, or if their spins are tilted and misaligned with their orbit, the final burst of gravitational waves shoots out more powerfully in one direction. Like a rocket expelling exhaust, the new black hole is flung in the opposite direction, a cosmic cannonball born from the recoil of its own violent birth. Simulations reveal these kicks can reach thousands of kilometers per second, more than enough to overcome the gravitational pull of even the largest galaxies. A supermassive black hole, the very anchor of a galactic core, could be violently evicted, sent wandering into the vast, dark emptiness between galaxies. This discovery forces us to reconsider how the largest black holes grow. If frequent, powerful kicks eject them during galactic mergers, it could limit their ability to accumulate mass over time, solving a puzzle about why some early supermassive black holes are not as large as we might expect. The dynamics of a galactic nucleus would be profoundly altered by the sudden, violent departure of its central gravitational heart, potentially disrupting the orbits of nearby stars and halting the growth of the entire galaxy. What does it mean that the universe can exile its most massive objects? It reveals a cosmos in constant dynamic motion, where even the most powerful gravitational monsters are subject to the recoil of their own cataclysmic interactions, creating a hidden population of lone wanderers drifting forever in the intergalactic void. A tiny dark heart beats in rhythm with its colossal galactic body. The discovery of the black hole bulge mass relation revealed a cosmic lockstep that defies all intuition. Across the vastness of space, in galaxy after galaxy, astronomers found a precise mathematical link. The mass of the central supermassive black hole, an object millions of times smaller than its home, is perfectly proportional to the mass of the galaxy's central bulge, the dense cloud of stars surrounding it. This is not a loose trend. It is a tight correlation, a fundamental rule written into the architecture of the cosmos. How can a pinprick of ultimate density, a mere speck at the center, possibly know or care about the weight of billions of stars so far away? The answer lies not in a single moment, but in a shared history of growth spanning billions of years. The black hole and its galaxy did not form independently. They grew up together, their fates intertwined in a symbiotic dance. This co-evolution is governed by a delicate balance of creation and destruction, a process known as feedback. When the black hole actively feeds, it does not simply glow as a quasar. It can unleash tremendous winds and powerful jets of energy that surge through the galactic core. These outflows act like a cosmic thermostat. They heat the vast reservoirs of cold gas within the galaxy, or in some cases, blow that raw material entirely out into intergalactic space. Without this cold gas, the galaxy cannot form new stars. The black hole, in its most active phase, effectively quenches star formation, putting a decisive brake on the growth of the very bulge it is correlated with. This feedback loop ensures that neither the black hole nor the galaxy can grow out of control. A larger bulge funnels more gas to the center, feeding the black hole and igniting its powerful feedback. That feedback then shuts down the gas supply, starving both the black hole and future star formation. This self-regulating cycle explains the perfect proportionality. They are not just roommates, they are partners, each setting a limit on the other's ultimate size. This relationship has become a cornerstone of modern astronomy, a fundamental link between the physics of the infinitesimally small and the structure of the impossibly large. It reveals that to understand the grand story of galaxy formation, we must first listen to the silent, rhythmic pulse of the dark heart at its center. This profound link between gravity and heat rewrote the rules of reality. Jacob Bekenstein, a young physicist, made a startling connection. He realized that if you throw a hot object, something with high entropy and disorder, into a black hole, that disorder seems to vanish from the universe. This would violate the second law of thermodynamics, a sacred rule that says the total entropy of the cosmos can never decrease. Bekenstein proposed a radical solution. What if the black hole itself possesses entropy? He argued that a black hole's entropy is not tied to its volume, but to the surface area of its event horizon. The larger the horizon, the more potential disorder it can hide. This idea was initially met with resistance, because if a black hole has entropy, it must also have a temperature, and everyone knew black holes were supposed to be perfectly cold and black. Then Stephen Hawking performed his famous calculation. He discovered that black holes do indeed have a temperature, an incredibly faint one, due to quantum effects at their boundary. This Hawking radiation provided the precise temperature needed to complete the picture. The two insights merged into the Bekenstein-Hawking formula, a simple yet profound equation that defines a black hole's entropy. It states that the entropy is proportional to the area of the event horizon. This means a black hole is the most efficient storage system for information in the entire universe. It holds the maximum possible entropy for its size. How can a simple area encode so much complexity? The answer suggests that the information about everything inside the black hole is not stored throughout its volume, but is instead painted onto its two-dimensional surface like a cosmic hologram. Each tiny, fundamental unit of area on the event horizon, a region trillions of times smaller than an atom, holds a single bit of information. This formula is a direct bridge between the worlds of the very large and the very small, a crucial clue in the quest for a theory of quantum gravity. It tells us that the smooth, continuous spacetime we experience may be an illusion, emerging from a vast network of discrete quantum information bits living on a boundary. The universe, in its most fundamental description, might not be three-dimensional at all. What we perceive as depth and volume could be a projection, a holographic movie playing on the distant screen of a black hole's horizon. This single formula does not just describe a black hole. It hints at the underlying architecture of reality itself, where gravity and thermodynamics are two sides of the same cosmic coin. The faintest of whispers might follow the thunderous collision of black holes. After the main gravitational wave signal from a merger fades, some theories suggest there could be a series of repeating, ever quieter echoes. These are not echoes in the traditional sense, bouncing off a solid wall. Instead, they are theorized to be gravitational waves themselves, trapped and released by a potential quantum structure just outside the event horizon. This idea fundamentally challenges the classical picture from general relativity, which describes the space around a black hole as a perfect, empty vacuum, smooth and featureless all the way down to the point of no return. If these echoes are real, they would imply that the event horizon is not the simple boundary we have long imagined. It might be surrounded by a region of intense quantum gravity, a fuzzy, high-energy zone sometimes called a quantum wall or a firewall. This structure could act like a semi-permeable membrane, temporarily trapping the ripples of spacetime before allowing them to leak back out into the universe in a fading, rhythmic pattern. The hunt for these signals is a meticulous process involving powerful computers sifting through the LIGO and Virgo data long after the main chirp of a merger has passed. Scientists search for subtle, repeating patterns that stand out against the random noise of the cosmos. A confirmed detection would be revolutionary, offering the first direct experimental evidence for quantum gravity. It would mean that Einstein's sublime theory, while stunningly accurate, is ultimately an approximation that breaks down at the very edge of a black hole, where the quantum nature of spacetime becomes undeniable. What would it mean if the void itself has a texture, a tangible structure that rings like a bell after a cataclysm? The search for these gravitational whispers is a direct probe into the fabric of reality, testing whether the universe's most perfect darkness is truly as smooth as we believe, or if it is etched with the faint, fundamental grain of quantum spacetime. Information may have found its secret passage out of the ultimate cosmic prison. Recent breakthroughs in theoretical physics are converging on a potential resolution to the black hole information paradox, suggesting that the universe does, in fact, preserve its history. The key lies in the strange nature of Hawking radiation itself. Rather than being purely random, this faint evaporation is now thought to carry a subtle, scrambled imprint of all the information that ever fell into the black hole. It is as if the event horizon acts as a cosmic supercomputer, performing an incredibly complex encryption on everything it consumes, then slowly leaking that coded message back into the universe. This process preserves the sacred rule of quantum mechanics, that information is never truly destroyed, only transformed. The most compelling evidence for this comes from a concept known as entanglement islands. Imagine the interior of a black hole is not entirely cut off from the outside. These theoretical islands are regions deep inside the event horizon that remain quantumly entangled with the radiation escaping far outside. In a profound twist, calculations show that the information we thought was trapped deep within the abyss actually contributes to the entropy we can measure from the outside. It is as if the interior of the black hole and the distant Hawking radiation are connected by invisible quantum bridges, ensuring no information is ever truly isolated or lost. This means the event horizon is not a stark, one-way barrier, but a fuzzy, dynamic surface where the distinction between inside and outside blurs according to the laws of quantum entanglement. While the exact mechanism of how information makes its journey remains a vibrant and active area of research, the mathematical consistency of these ideas is a monumental step forward. They strongly suggest that quantum mechanics remains valid even in the face of a black hole's overwhelming gravity. The potential resolution of this decades-old paradox does more than solve a puzzle. It reinforces a beautiful and powerful idea that the laws of physics are universally consistent, holding true from the smallest quantum particle to the most massive gravitational giant. These discoveries are weaving gravity and quantum theory into a single, coherent tapestry, bringing us closer than ever to understanding the fundamental language of the cosmos. From a ghost in the equations to a shadow in the telescope, the journey to understand black holes has rewritten our cosmic story. These 30 discoveries have transformed these objects from theoretical impossibilities into fundamental pillars of modern physics. Each revelation, from Hawking radiation to the holographic principle, has forced a profound shift in our thinking, challenging the very definitions of space, time, and information. Black holes are no longer just endpoints of collapse. They are dynamic engines, galactic architects, and the most stringent laboratories we have for testing the limits of our knowledge. They have stretched the theory of general relativity to its breaking point and revealed the deep, unresolved conflict with the quantum world. This ongoing tension is not a failure of science, but a beacon, illuminating the path toward a deeper truth, a future theory of quantum gravity that will unite the very large with the very small. The journey is far from over. With every new gravitational wave we hear and every new simulation we run, we peel back another layer of this profound mystery. Let these insights be a starting point for your own wonder. We would love to hear which discovery reshaped your view of the cosmos the most. Share your thoughts in the comments, and if you are eager for more journeys to the edge of understanding, subscribe for our next exploration into the universe's greatest secrets.